The recording will appear on Zoom later. Okay, so if somebody's watching this later, I'm just answering questions for the next 20 minutes, and then at 10:50, I'll give a few tips and things, kind of at the official start time of class, but then we'll just continue. Probably easier to watch this recording than the Panopto, because this will be uninterrupted. So yeah, particular questions from anybody here or the one person that's online here, you can put it in the chat. Yeah.
Did you spring 2019?
Yeah, let's do it. Any other questions people want to yell out while we're sitting here? So something to do with curves, something to do with lines and planes, probably, maybe not. Let's go take a look. So spring 2019. To be. Is this the right one? This translation question. Find the equation of the surface consisting of all points such that the distance from the point to here is equal to the distance from the point to the XY plane. So I do all these the same in that I look for, so part of the problem is we're working with a general, we're talking about a condition. I think that confuses, it can be confusing to folks, but if I give a point 1, 2, 5 as an example, let's just talk about that for a second. And I say, what's the closest point on the ground? What would that be? Just for that example, for the 1, 2, 5, the corresponding point that's directly below it on the XY plane, what would that be? It'd be 1, 2, 0. In general, it's kind of easy to find because you just say, this is what it means to be on the XY plane. This is what it means to be lined up with that point. That's how you think about it. So I find that very helpful. So if I wanted to know the distance from this point to the XY plane, it's going to be this, 1 minus 1 squared plus 2 minus 2 squared. Now, you don't even need the formula. You might be able to see from the picture that it's already 5. But the point of that is that's a general approach. You're looking calling that the corresponding point method. So if you can figure out the corresponding point, you don't need a special distance formula. You can just use the regular distance between 2 points formula. So same would go like if I wanted to know the distance to the z-axis. So here's how I think through it. If I walk straight over to the z-axis, what does it mean to be on the z-axis? These are both 0. And what does it mean to be straight over from 1 to 5? This is 5. So I just like the uniformity of problem solving for these sorts of things. So this would be this way. So anyways, now what we're actually doing in the problem is we don't know what the numbers are. We're just giving the conditions. So if I change this to X, Y, Z, and they give me the following. So now let's translate. I want the distance from X, Y, Z to be equal to the distance from X, Y, Z. And if I was doing this, I wouldn't say X, Y plane. I would just write down the corresponding. So just like we did with the 1, 2, 5, what would be the corresponding point on the ground if this is an X, Y, and Z? Well, if it's on the ground, this is 0. If it's in line with it, this is X, Y. Does that make sense? That's the key piece. And then from there on out, we're going to write that out. So it's the square root of X minus 0 squared plus Y minus 0 squared plus Z minus 2 squared equals the square root of X minus X squared, which is 0, and Y minus Y squared, which is 0, and Z minus 0 squared. So at that point, we've done it. We found the equation. Let me take it one step further. So we have x squared plus y squared plus z minus 2 squared. What the problem is claiming is that this is something that has a name. So now we're going to switch gears to trying to name it. That doesn't look like one of our 7 named things. So I need to simplify it in hopes that I can recognize it. So let's try that. So let's go here, simplify. Let's square both sides. And there's a temptation at this moment to try to say it's a ellipse or something, but the problem is it would be an ellipse if the thing on the other side was a number, but since it's a variable, I need to keep going. I don't recognize what it is yet. So the key moment is you got to expand. This is going to be z squared minus 4z plus 4. And that's very important because what happens? Something cancels. What happens? The z squared cancels. And then I don't care how we write this out. You can leave it like this. You can simplify it. But at this point, we're at a place where we can name it. So you can either do the traces or thumb method, or you can kind of do the table method. We have 2 things that are squared and one is not. I would do the traces method, because I can do it quickly. So in my head, I'm thinking if I cover up x, so I think some of the confusion is about the other numbers, but no matter what the other numbers are, what shape is that? When in 2D, when one variable is squared and the other one's not, what is that? Parabola. So that's the key step, is it looks like a parabola from x's perspective. It looks like a parabola from y's perspective, meaning if you replace it with a constant. And so then the name is paraboloid. That's always the case when 2 are squared and 1 is not. But then we need the adjective. It's circular. Yeah. So if you get rid of the z, you get x squared plus y squared minus something plus 4. And that looks like a circle. It'll depend on the constants what the radius of the circle is, but it's circular. If there was a minus between the x squared and the y squared, it would be hyperbolic. Those are the 2 possibilities. So there's kind of 2 skills there. One's the translation skill, and one's the parabola. Anybody else questions on this, on the surface naming? Yes, please. Yeah, we could look at that for sure. Any other questions on this one? If somebody online has a question too, you can ask in the chat. And I see there's another question there. Spring 24 3B. So I'll come back and look at that in a moment. Yeah, since we have this open, let's look at this other one. And this is all coming from spring 19. So let me make a note to that. Spring 19. Okay, so let's move forward. You can stop me at any point. And people online can raise their hand online, or you can unmute. So this is more of a kind of a conceptual problem. When I see this a problem like this where they don't actually give me the vectors, in my head I'm thinking, okay, I'm gonna need to use our facts. So let's maybe start to collect our facts. We have a few. We have A dot B is the most important one we use the most. Cosine of theta. That's our 10-star fact. And that's provided there's a key thing in there. What does that theta mean? It's the angle between them, but in particular when they are tail to tail. So that's often an issue in these problems. Other things, we know that the cross product of the two vectors, if you take that magnitude, we don't use the second one as much for a few different reasons, because it's harder, it's longer to compute cross products. And when you do inverse sine, you sometimes get negative angles, so cosine's a little nicer to work with. Just a couple things. And then there's one other fact, which is that this has a geometric interpretation. What is it? It's the area of a parallelogram. So a problem like this, a general problem, what's asking us like about it without giving us, those are the things that would be kind of front and center in my mind. If we really get stuck, you could like make up vectors and like do an experiment. But the few things jump out to me. There are three different questions here. So the first one says, what's the dot product? But I'm not telling you the vectors. And so that's when I would look and say, well, what am I going to do? I know this. But in order to use that, I would need to know the length of U, the length of V, and the angle between them, if they're drawn tail to tail. That's really what that question was about, was based on the information, we know the lengths of the two vectors and the angle between them. What's the lengths? 3, it was hiding up at the top. And what's the angle between them if you draw them tail to tail? Now they're already drawn tail to tail, so that's good news. And it's an equilateral triangle. So it's 60 degrees. So this is going to be 3 times 3 times cosine of 60 degrees. Cosine is the x coordinate on the unit circle at 60 degrees. And at 60 degrees, the x coordinate is smaller than the y coordinate. So it's 9/2. Is that what it came out to be? Good there. I remember this exam that this one caused people the most trouble. So maybe let's do that one last. The area of the triangle is 1/2 the area of the parallelogram. So that makes me think of that other formula. So in my head, I'm thinking, well, since we just talked about UV, why don't we use those again? We could use 2 other vectors, but this is what I'm thinking. And that is the same as the magnitude of U, magnitude of B, sine of theta. And it's the same angle, 60 degrees. So it's going to be 1/2 times 3 times 3 times whatever sine of 60 degrees is. So it's 9√3/4. That's kind of a specific question, but it was about using those couple facts. Yes. Yeah. Yeah, so the issue here is that they've already drawn a representation, but it's good to realize that vectors are free to move. Meaning I could have drawn U like this. I could have drawn V like this. I could have drawn V like this. I could have drawn W like this. I could have drawn W up here. Those are all still the same vector. So we have to recognize that the picture they drew was just one possible way they could have drawn it. And so if I was talking about U and W, and I wanted to know the angle between them, I would want to grab the W vector, grab the U vector, and put them tail to tail. Now, when you do that, what's the angle between them? It's not 60 degrees. So the reason you had to do a little bit of kind of geometric reasoning. If you want, I think a few people asked me about this around that homework. So these 3 angles, can I convince you they're the same? And since that one's 60, the other 2 are 60. So it was 60 plus 60. So that's why it's 120. So the angle between these 2 vectors is 120. I don't think that came up here because I only asked about UV. Yeah. And let's finish up that other part. So the part I remember when I wrote this question, I was originally going to ask, what is the length of u plus w? But I thought that I remember thinking, well, that might be too short. But let's do that first. What is the length of u plus w? This is a different fact. It doesn't have to do with dot products or cross products at all. It has to do with how we think about the sum. What is u plus w? Visually. So let's erase here. In my mind, there's three ways to think of a sum. So if this is u and this is w, I'll just put it here. You can think of it as the direction you get pulled if both of those happen, meaning this direction. There's u plus w. But there were two other interpretations. Well, one was called the head to tail rule, and one was the parallelogram. So what's the head to tail rule look like? You take w, you move it over here. The parallelogram rule will look like this. So with all that being said, what is u plus w? It has another name in this problem. It's actually already drawn on the page. U and w are already head to tail. So u plus w is what? V. So this picture shows an example of a vector sum. U plus w equals v. So this is the same as the magnitude of v, which is what? 3. So I was originally going to ask that question, and I was like, oh, it's kind of too short. How could I ask another skill? Well, let's just multiply it by 2 and see if they know how to factor it out. And that led to lots of confusion. So that was an unintended, became harder than I thought it would be because of this step. So you had to factor out 2 and realize that just makes the vector twice as long as whatever it would be. So that was really a different skill. But I remember that ended up being quite challenging. Okay, let's see where we're at time-wise. So 10:50, I'm going to stop briefly. So in a minute, I'll stop briefly. Let me look here at the method for question 1. So there's a few different questions. I'm going to come back to our page. We've just been doing these couple problems from the spring 2019 exam, anyone that's joining online. But since it's 10:50, I'm going to switch over and say a few general things. So far we've done this, rid of it. Oh, I don't want to get rid of it. I just want to move it. Just to kind of help me keep track of where I'm at. So we did this and we did this, and I would say one of them was distance and naming. And then one of them was vector facts. And sometime later today, once the video processes, I'll try to make some timestamps. Okay, so a few different notes, and then I'll kind of peek through. So start to think about what your questions are going to be. It's nice if you give me particular old exam questions, but I want to spend a few minutes just saying some general things we should know. Because I find if I do an open review, people find the hardest questions from the last 20 years, and everyone leaves crying. So I want to make sure we get some of the fundamentals down. So your exams tomorrow, I do have like my inbox is kind of exploded with various things that are going on. I will go back to my office and reply to all those. I copied the exam and everything. So if you've emailed me about some remote issue, I will reply to you within the next few hours. If you're somebody that has DRS accommodations, the exam has already been delivered to the DRS office. If you're in the process of still getting those accommodations figured out, I would visit the DRS center today. Okay, so anyways, exam tomorrow, it has how many pages? 4 pages. So this is something, because time is kind of a crunch in this course on tests, I've started to be very precise about where things are so you can plan your exam time. So what's on page 1? 12.1 to 12.4. So the sorts of things I'm thinking there are, find the equation for a sphere. You know how to do that. Find when a sphere intersects the xy plane or the yz plane. I think you did a little bit of that in the test prep. We also did some distance. Find the distance to the x-axis or the distance to the yz plane. And then we did a bunch of vector facts. So working with vectors in 2D and 3D, that was 12.2. 12.3 and 12.4 were dot products and cross products. So there will be, that first page will be more of somewhat of a random collection. Sorry, I know this is too small. But there will be things there that definitely are straight from the homework or from test prep. So if you've been doing the things faithfully, there will be things you've seen fairly clearly. Maybe other things we have to adapt a little more. Okay, so then this page is going to be about 12.5 lines and planes. My intention is to sort of have two parts. Find the equation of the line, find the equation of. So that would be great. And during the review yesterday, we did a few of those. And then this page will be, I'm thinking of it as 12.6, 13.1. Those sort of go together because oftentimes the way we visualize the curve is at the intersection of two surfaces. If I ask a question about a surface name, I basically say, what's the name of this surface? We can talk about that. And then we have this sort of computational piece, working with curves. So for that, I could ask about what's the arc length at a particular value, or set up the arc length, what's the curvature, what's the tangent line, those sorts of questions. So in terms of studying, I've given a little bit of this, but I'm going to show one thing. So during the review session yesterday, a few people said, well, where's the exam archive? So there's several links to it. That worries me. Have you found the exam archive? Yeah. So find that exam archive. I'm not trying to hide it. There's a link in the module right here. But hopefully you've been spending a little bit of time on my review page, because if you're struggling with, like, these are individual practices on certain topics. So if you're struggling with 13.1, 13.2, you can try that. So there's more practice there, but the exam archive is probably your best place to go. And I would focus on recent exams. And then if you need more, you go further back. Okay. And I have little recaps there. But no matter what, we got to dig in and actually do some problems. So in a moment, when I ask for questions, it's nice to ask specific ones here. Okay. The other thing is, let me think of a couple specific things. You're probably going to have to compute a cross product at least twice on the test, because it comes up in several formulas. So do you remember how you can check your cross product? It would be nice if before the exam was done, you went back and checked
by
this.
the cross product by the one of the other like vectors, right? To see if it go.
Yeah, that's right.
Because it's like.
Let me close this outer door. I'll turn up my volume. Yes. So once you do the cross product of two vectors and you get something, I'll just make something up. You check that this is perpendicular to this and this is perpendicular to this. And that's pretty quick to do. That means the dot product is 0. So I just like to say that because if the cross product is step 1 in some calculation, it's painful to mess that up. And it's really nice that you can check and be sure that those are 0. Then you can be confident moving forward. So check your cross products. Check your equations for your lines and planes wherever possible. Like if it says give the equation of the plane that contains this point, you could check at the end that it actually contains the point. So build a few of those things in what you're doing. If you get stuck on a question, like you can't solve something, tell me in words, I can't solve this, but I'm going to show you the rest of the work. I'm going to make up a number. So treat your exams a little bit more like an essay question. Don't leave it blank, because what score does a blank question get? 0. If you write a bunch of nonsense, that might not get points either. But if you leave it blank, it's 0. So I just want to change your perspective. Give me the opportunity to give you points. Okay, so let me look. Any general questions about that? So I would give yourself about 15 minutes a page. Yeah, question in the back. Approximately, I try to make the midterms about 50 points. And so it'll be like, the first page might be 12 points and 12 points. Maybe one will be 14 points. So it's about, yeah, about 12 points a page. Other questions? Yeah. It's typically 1 point. There's always this problem of sometimes a small error dramatically changes a problem, which doesn't allow you to show some of the other stuff. That would be the time when it'd be worth more. But typically that would be 1 point. There are times when even it's just a half a point. Sort of depends on. I've seen people just miscopy. That's the sort of error I make. These are all good reasons for you to show what you're doing. I mean, if you just give the correct final answer and there's no work anywhere, we don't give you credit. So you got to give some work. But the reason you give work is because then I can figure out what went wrong, if something went wrong. Okay, so let's see a little bit of what I just want to make sure I didn't miss, and then I'll open up and answer a few more questions. So somebody asked about spring. I'll move this back up. We're just going to do what we can do. I find that there's a little bit of I try to avoid this feeding frenzy. Oftentimes people get mad because we don't get through more questions, but we got to do this with some quality here. So can you please go over the method for spring 24? And I'm just going to get these written down, what people have asked in the chat. Oops, I didn't get to your question, Sabrina. Hopefully that comes up again. Could you please go over how to use the projections? And then any particular other questions that somebody who hasn't offered one yet that you really want to see, or a topic. If there's a topic you're worried about, it's nice to find an old exam question we can work from. Yeah. 3B, thank you. Well, let's start with those. And one thing I like to do is as we go through them, we will scan through the other questions. So let's go to the spring 23. And that's right here. And I just like to pretend that I'm taking this test right now. So I write down my name, my info. Your cover sheet will be the same setup. And then I see this first question. So I feel like as a student, I'm wanting to absorb as many. I'm like, would I know how to do this? Are you not able to hear? Somebody says they're not able to hear. Hello? Can you hear me? Okay, thanks, Katie. It's going to be a little awkward because I'm using the remote for the classroom and then my computer is recording my voice. So I think it shows me it is coming through. So check your sound on your end. Area of the parallelogram, what's that about? Cross product, 1/2 the magnitude of some cross product. Oh, not 1/2. That'd be the area of the triangle. So I'm going to find two vectors for two sides and do the cross product. So this is kind of what I like to do as I'm studying. I want to keep saying, which things do I not know how to start? How do I make a vector length 5? Can you remember how you do that? You make it length what? You always start by making it length 1. How do you make a vector length 1? Divide by its length. And then if you want it to be length 5, you multiply by 5. Okay, that's something to do with a projection. How do I know? Because it says perpendicular to some line segment. So we can come back. Somebody mentioned that. So I find this sort of studying is a nice added piece to going through details. A question about lines and planes. Okay. think your question was 3B. Right here. A question about intersection. I did that during my other review. Okay, is this it, Lexi? Okay, great. So let C be the curve of intersection, and sorry if it's too small here. And let me do this. Is this gonna work? No, it's not. I don't really like how OneNote works, but it's harder when I have the Zoom window open. Okay, curve of intersection, I'll just write a little bigger so we can see it, of these two things. And it says these are both surfaces. And it says we want to know the arc length. I'm just going to make it bigger so you can see. If you go from the point 0, 0, 0 to 3, 9 halves, 9 halves. So if you found the intersection of those two things, the length. So let's think through the issue. We have a formula for arc length. It looks like this, the integral from A to B of the square root, and it has these pieces. But what we need to put in here is x prime of t, y prime of t, and z prime of t. So we immediately have an issue. What's the issue? The issue is we don't have a t. We don't have anything to take the derivative of. I actually need to describe the curve in terms of one variable, one parameter. So this question is less about arc length and more about this other skill. What's the other skill? It's parameterizing. So this right here is a cylinder. This right here is something I don't know what it looks like. We want to study the intersection, and so our job is to come up with something, anything you want, here, here, and here, that depends on t. And the only rules are that the second one has to be half of the first one squared, and that the z has to be 1/3 of x times y. So this is a practical example of when you want to compute something with an intersection, you have to find this. Okay, so what do you want? So the way we parameterize is first we ask, is there a circle? Do you see a circle there? My answer is no. If I do see a circle, then I would use a circular parameterization because that tends to be easier to use. So just a recap there. So if one of my things was a circle or a cylinder, circular cylinder, I would use that parameterization. I'm not going to do that here because there's no circle. So then plan B. I'm going to randomly pick a function of t and shove it in for one of these variables. Some choices might be better than others because it's easier to solve for the other variables. For example, if I call this t or t squared or t cubed, I don't know how to get x and y from that. So I'm not going to have z be t. If I make y be t, then I'm going to have to do the square root to solve for x. So I'm not going to have y be t. What do you think I should have be t? X. So I'm going to have this be t. And you can pick some other function, but t is kind of the most basic starting place. That forces this to be 1/2 t squared. And that forces z to be what? So this is t. And this is 1/2 t squared. So altogether, what do we get? A half times a third is a sixth. T to the third. That's really what the question was about, was parameterizing. And now this is, I mean, what I like about this question is at least, it really shows you why we do that sort of thing, so that we can compute, so we can get it into our integral. So now I'm going to take the derivatives. 1 t, what's that last derivative? 1/2 t squared. So I brought down the 3, subtracted 1, brought down the 2, subtracted 1. Because one other thing is, what in the world are the bounds? It said to go from here to here, but how do I get the t? An important little skill note. So somebody tells me that this is 0, and this is 0, and this is 0. What's t? 0. So the starting time is 0. If somebody tells me that, so that's always going to depend on the choices you made for your parameterization. But if somebody tells me this is 3, and this is 9/2, and this is 9/2, what's t? 3. That's it. Did
I have
this
a
one have?
question.
Darn it. I was mean that quarter. So if we are having to compute this, then that means I chose everything to work out so that the inside factors. Yeah, Katie.
Wait, question. So,
Mhm.
it's clear that like when we parameterize the the values that we have for our points kind of match up to them exactly. So is that like a kind of way to check, like if you parameterized wrong, like it will not work?
That's a good point. So she's saying that if we had parameterized incorrectly and we plug 3 in here and plug in 3 here and we don't get these numbers, something went wrong. So that's a nice little check. I had to, so when I wrote this question, I had to make sure. So if they don't match up, it either means your parameterization wrong or your instructor made a typo. So either way, it's something worth asking about. But that's something I check. Yeah, good point. Other questions on that? Was your question about the computation? Okay, so computation piece is then, I'm just hoping that everything under the radical simplifies. If you have in your mind that everything simplifies, it makes the problem easier. Because basically, I know that this is impossible for us to do unless that factors. So I remember on the discussion board, some people having trouble with this 4. You don't even have to think about it. You could immediately attack the problem now, meaning, is it a perfect square? Like I said, I wouldn't necessarily look at that and go, oh, that's a perfect square, but that's the only way, it must be that way or we can't do this problem. So in order for it to be a perfect square, you'd have to take the square root of 1, which is 1. In order to be a perfect square, what would the other term have to be here? What's the square root of 1/4 t to the 4th? It's 1/2 t squared. And then we're going to cross our fingers and hope that that does indeed factor it. Let's check. We're going to monkey face it out. There's the eyebrow, nose, mouth of the monkey face. And we get 1 plus 1/2 t squared plus 1/2 t squared plus 1/4 t to the 4th. Does that match up with what was under the radical? Yes. So that's what we get. That was that homework question, how we did that. Now, at that point, there were a couple people asked me questions about after that step. So what happens after that step? Let's do that a little bit. So it's the integral from 0 to 3 of 1 plus 1/2 t squared. So what happens next? Now we get to flex our calculus 2 muscles. We don't have to flex them too hard. Antiderivative? Okay, tell me the fraction that comes next here. 6th, yeah, because we integrate, it becomes t third over 3 from 0 to 3. So it's going to be 3 plus 3 cubed over 6, which, because I'm too lazy to get my calculator out, I'm going to write in a weird way and cancel a little bit. 3 plus 9/2. So 15/2. Is that what it came out to be? 6, 15. Don't trust me. If I was doing a test, I would calculate it more carefully. Okay, that's kind of a side, the end of that question is a side thing. To me, the big idea there was getting used to the idea that how we work with a parameter. Lovely, thanks, Elijah. Lexi, we good? Okay, let's pop back here. So that I would call arc length. Cool. Normally during these sessions, I'm running around I used to have students bring copies of paper exams, and then I would run around the room and grab them from people. This is a lot less exercise for me. That's probably bad. Okay, let's look at spring 24. So I just want to make sure we've hit a few topics here. And on the discussion board, I posted the recording of yesterday with a timestamp of what we looked at. So I'm just hoping we hit a variety of topics. Spring 24. We're going to go till 12:30. And I'll record all this and post it. I can't remember. If I click away from a page, I can't remember what it said. So I'm gonna need your help. Spring 24, question 3. Our professor slowly lost his mind. Okay. This one? Good. Who asked this one? Is it online?
Yeah,
Maybe?
I asked it online.
Oh yeah, thank you. You were asking about part B, is that correct?
Yeah.
Okay, so part B is a kind of more of the same. I can say something about that, but just to give us a change of pace, I'm going to force us to look at part A first. This was not your question, but it's a fairly quick question that will hit on a couple topics that I don't know that we've hit elsewhere in my reviews. So let's play this game. So it's a open review with my executive decisions to adjust things slightly in a few places. Okay, so let's look at that question. It just comes out too small because of the page here. Turn it. Let's go one more. So let me write what this says. It says you're given some 3D curve. So again, that means x is the square root of this. That's the way an algebra student writes it. This is the way a calculus student writes it. And then we have y is this. And we have z is this. So we've learned that sometimes we write it as a vector for various reasons, to think about it as a position vector. Sometimes we write it as a location. We think of those as the same thing if we're just talking about the curve. Okay, so secondly, find the tangent line to the curve at this point. So I like that question because I know it's coming, because this professor telegraphs his passes and said that it would be here, something about tangent lines. And so I need a point and a direction. In particular, I need the tangent direction. But they did not tell me what t is. So I remember that being one confusion about this problem. And there is another part to this question, but I'm dealing with the first part now. So how would I find the t that goes with this? Can anyone find the t? What do you get? 2. So you found that this was 3. This needed to be, this needed to be 1. This needed to be 8. And so you figure out which one of those you'd like to solve, and you hope that the others match. And I think this is probably the easiest to solve. The cube root of 8 is 2. And then I do a quick check. Let's use Katie's method of making sure. So you put the 2 in the other ones, and you go, well, that does give me a 3 because it's the square root of 9. I put a 2 in the other one. It gives me e to the 0, which is 1. Hooray. So t equals 2 is the time. So the location is 3, 1, 8. And if you ever forget, that's the location at 2. That's what I just put in there. How do you get the tangent direction at 2? What do we need to do? We need that derivative. Okay, so this question has a little bit of derivative skill practice. So compute those 3 derivatives. I'm sure that was part of what I was testing here.
Wait, sorry, just to clarify. So because they're asking for tangent line in this case, to find the value of kind of the vector that we're going to be putting in front of the t in the parametrics, we need to find first the derivatives of each of these equations.
That's right. Yep.
Okay, okay.
Yep. We need, in general, if the word tangent appears in a problem, you will very likely take a derivative. So we definitely, but in this case, we want the tangent vector. So there's a difference. I think sometimes people get confused on a question like this. There's a difference between the tangent vector and the tangent line. But we need to find the tangent vector in order to get it. Okay, so what are the derivatives? The first one is the 1/2 comes down. The new power becomes -1/2. I'm going to make 2 mistakes because I remember grading this question. So I remember that being a common derivative people wrote down. There are 2 mistakes there. Do you know what they are? The chain rule. I forgot the chain rule twice. So the derivative of the inside here is what? 4. The derivative of the inside here is 2t. The chain rule is just a part of everything we do. At this moment, I like to become an algebra student again. So I would do 4/2 is 2, and then I'd rewrite this as a fraction. I don't like to be a calculus student for very long because calculus students write things in ugly ways so that they can use their derivative rules. But when I'm going to evaluate something, I like to write it this way. I don't often do that. In my head, I do that, but I just like to say that. So now I'm going to plug in 2. So I find it easier to plug in 2 here. So this is going to be 2 over the square root of 4 times 2, so square root of 9. This is going to be 2 times 2 e to the 0. This is going to be 3 times 2 squared. So it's 2/3 is the first one. 4, 12. Usually we put a t here, and I'm perfectly fine with you putting a t there. If I was doing this myself, though, I don't know what I did in my solutions. But nowadays, I like to put a u here. That's just a matter of taste because t is already in use as a parameter for something else. So if I'm coming up with a new parametric equation for something different, I find it much less confusing if I use a different letter. If the question is just asking me for that, it doesn't matter. You just, with the t is fine. Okay, so that was the main piece of that question, is realizing that, and I think in the homework you had to do this in a couple different ways. One question asked you to actually think about this vector. Like the harder of the questions in the homework was, I think you had to find when that vector was perpendicular to some other vector. That was that one question. But then you also had a couple that just said find the tangent line. Any questions on that? I think that's good for us to go through. Is there more to that question? Did I forget something? I did.
Wait, I have a
Yeah, go ahead,
question.
Katie.
For the x part where you have the 2/3 u,
Yeah.
is that, oh, that's from the, okay, yeah, sorry, I got it. It's from the other one. Yeah, okay. You just
Yeah.
Yeah, okay.
Yeah, good question. Other questions about where numbers are coming from? And you can yell out if you're in the room too. Yeah, so if someone gives me a parametric equation and then gives me a point, but they don't tell me what the t is, then you need to figure out when the first component is equal to 3, and the second component is equal to 1, and the third component is equal to 8. Oftentimes we can do that quickly because you solve whichever one is the easiest. So what happened, I'll write it out here so you can see it. This was 3. This was 1. And this, so this is one of the things about parametric equations is often we're using them to describe x, y, and z. So if you're given a problem with x, y, and z, you solve. Now, to me, the easiest one to solve is the third one because you can just do the cube root of 8, which is 2. Once I've solved that, I really don't need to solve the other ones unless I just love solving, in which case I could take the log of both sides. You get 0. You get t squared as 4. You get t as plus or minus 2. Oh, that was solvable. You square both sides. I do love solving. Subtract, you get 4t is 8. You get t is 2. We want the solution that works for all 3 of these. But it's overkill to solve all three when you just can solve one and check the others. Does that make sense, what I'm saying there?
So step one in a lot of problems is if they give you an XYZ point
And you're given the curve parametrically, set those X, Y's, and Z's to the X, Y, and Z components, so you can know what the corresponding T is. And sorry when I step away, you probably lose my audio here. Okay. So the other part of the question is, where does this intersect the following plane? I do tend to like intersection questions. I remember a couple years ago, someone wrote me after the test and said, you had 4 intersection questions on the test. There weren't that many in the homework. I hate you, Dr. Lovelace. They didn't say I hate you. That was my interpretation of it. But I just want to give it away. I like to ask about intersection because it forces you to put your things together. Because it's fine if we can find the equation of the line, but it's better if we can use it. So how would I use what we just did to find the intersection of the line with the plane? And actually, this is an relatively easy step. What do? We just substitute it in, that's it. So you go 3 plus 2/3 u minus 2 times 1 plus 4u. So if all we do is find the lines, that's not that helpful, I don't think. We expand it all out, we find u, and we're done. So 9 plus 2u minus 2 minus 8u plus 8 plus 12u is 33. What is that? 14, that's 6u. I just shoved those three things together. 14 minus 8. And then I'm going to do 17 minus 2 is 15. I'm putting these numbers together. And I'm almost there. 6u is whatever 33 minus 15 is. The way you get better at the arithmetic is you allow yourself to do it. So I've gotten better over the years because I make myself do it in class. Or for fun, you can pull this out. Oh yeah, anybody do this? I think my kids are always talking about regrouping. There's new words for everything. 3. So here is a comment. I remember when I gave this test, I had students use a T here. They did all of this correctly to that moment, and then they got the wrong final answer, which was so sad. Because they plugged this in up here because they forgot what their T represented. The T we're working with is the T from the line. And that's why over the years I've decided to just avoid that problem from the get-go. And when I have a new thing, I use a different letter, and then there's no confusion. So that's why I do that. Okay, so if you put in a 3 here, you get 3 plus 2 is 5. Put in a 3 here, you get 12 plus 1 is 13. Put in a 3 here, you get 36 plus 8 is 44. And 44 is the jersey number of which Mariner? Why did I say that? That has nothing to do with anything. Julio Rodriguez. Okay.
So that one had a couple things. An intersection, which I've got to do.
Part of it's messy because I was explaining as we go. Questions on that one? Is that all right?
Question, wait,
Yeah,
so
please.
so we find u, and then to get like the actual intersection point, we're plugging that back into like the original vector given to us, right?
Good question. So
Or
we get
is that what I'm
u.
getting confused on?
Yeah, so we want to plug that in here. If we find that's no longer refer, because the question is asking about which two things intersecting, the original curve intersecting the
Right.
plane or the tangent line intersecting the plane.
Tangent line.
Tangent line. So everything we're doing from here has nothing to do with the original curve.
Ah, okay.
Makes sense? Yeah.
Yes, okay.
Lovely. So we did part A. Do we want to look at part B or something else? How are we doing? Going until 12:30, so we have an hour here. Other things I could. So the question for yourself is, Well, the moment you see a tangent, what I'd be thinking is, if I get to a question on the test, probably on the last page, that says something about a tangent line, what are some things you can do? Take the derivative, like right away, you could take the derivative. And then in your head, you would say, okay, that's a tangent vector. I have the position. If I know what the time is, the tangent vector will go here. So it's good to just have that ready. So there's certain things when you go to take the test, you're sort of ready and don't have to spend time thinking on. Okay, there was a question about part B, so let's say a little bit about that. I hope that's okay. And sorry, I'm not doing it in a more organized way. I do these open reviews. My solutions in the archive, like this is, what is this? Spring 23 we're looking at? Let me show one thing real quick. Can everybody online see this? Katie, can you see what I'm showing now?
Yes.
Great. So my solutions don't look like that, so I apologize. It looks like, was this, am I not looking at the right exam? Spring 24. So if you want a cleaner solution, you're not going to get that during this time because I'm explaining. But this is what it looks like. So here I try to, you know, this is something I've put some thought into trying to write it a little cleaner. That was worth 6 points. Sometimes I have words where I edited it, but you can see I'm finding the t. I got the location and direction. I got the tangent line. I did the intersection. So it's good when you're kind of going through your solution to map out what you will do when you see this again. That's the sort of stuff you can put on your note sheet. Okay. So I just want to make comment on that because I feel bad about how poorly the solution looked. All right. So let's look at this next part. This is kind of nice because we're circling back to that question from before. We're spending a little too much time here because I would say that about 40 to 50% of the time I ask about arc length, and another 50 to 60 I don't ask about it. So it's kind of one of those toss up whether it'll be there or not. So we got to get, you know, give some other things our time. There's just a limited amount of space in the test. So find the arc length of the curve of intersection of this elliptical cylinder and this. So to me, this is an interesting question because it's saying if somebody gives you like a cylinder like this and you chop it off with a plane at an angle, can we find that length? If you think about it, that's actually a really hard question. The length of an ellipse in general is hard to do. There isn't a nice formula. The length of a circle has a nice formula, but this is in 3D. So even just writing down what this length is going to be hard, except we have a way. So this question is asking us to come up with some parameterization that walks around it. And so this is the game we're playing. There are multiple correct answers for this parameterization. One would involve a circular parameterization, even though there's no circle there. And one would involve randomly making one of the variables t. I think in the discussion board, I did it both ways. So if you want to see a full solution with both methods, that's somewhere on the discussion board. Can I find that? Just to show you the sorts of craziness I'm doing. This was spring 24. So just a comment about searching. You can go old exams, exam 1, and you can see where we've been. Spring 23 2C. Sometimes people don't label what they are calling it. Spring 24 1D. These are the questions that have been asked so far. Oh, hey, there it is. And so I go through and talk about a few different perspectives. There's a video. Here I do it again with T. So if you want lots more details, it's there. But let's talk about it. So the main issue is this. How do we adjust our circular parameterization if it's not a circle? And so let me give you a couple perspectives. So if somebody gives me a squared plus b squared equals 1, if I have a be cosine of anything and b be sine of anything, that will satisfy that condition for all values of t. Okay, let's step it up a notch. What if I make this a 9? Is there an adjustment that will give me the parameterization for a circle of radius 3 instead of radius 1? There's a small adjustment we can make. What is it? You put a 3 here, because you get 3 squared plus, so you factor out the 3. So if you're lost on this comment, this squared plus the same thing squared is going to equal, you can factor out the 9, you get cosine squared plus sine squared, and you get 9. You don't have to think through that. You can just know that's the radius. Okay, so then the last step of the puzzle, what if it looks like this? So we're going to say this over 9, this over 4 equals 1. That's an ellipse. There's a way to make an ellipse look sort of like a circle. And the way you do it is you factor it in this way. This would be a 3. So now my question is, what do we want to replace? We've actually already answered this question. What would I want to replace this with? And what would I want to replace? I think this is, sorry, I'm taking a little bit of time here, but I believe this is where the confusion, one of the confusions that happens a lot here. So I'm going to replace a over 2 with what? Cosine. And b over 3 with sine. So when I see this question, I have a few different thoughts. But one is, it kind of looks funny. I feel like I'd like to write it the way we normally write an ellipse, which is this. You don't need to do this to do this problem. But that's how an ellipse is often written. So how did I get that? I divided everything by 4. And in my head, I'd be thinking this. And so I go, oh, I can use a circular parameterization. I just need to make x equal to cosine. And I need to make y over 2 equal to sine. And then we usually multiply both sides by 2. This is back in my 13.1 lecture. I had a page where I talked about the general parameterization of an ellipse. There was just a formula on there. Okay, so that was kind of the tricky piece. The one thing is you can check. You can plug this in here. You can plug this in here and make sure it comes out to be 4. Okay, once we've done that, we've done the hard part in my mind, because what is z? Z is the square root of 3x. And so what do you get? Let's get rid of this here. So z is going to be the square root of 3 times whatever x is, which is cosine. So this is the preferred parameterization because it's simpler. It doesn't involve square roots. This would be my preferred way to compute this arc length. But let's see if we can finish it out. What would be the derivative? So here you'd have a negative sine. Here you'd have a 2 cosine. Here you'd have a negative square root of 3 sine. I remember a lot of students asking about the bounds. How would we know the bounds here? So a little bit of, based off of the description, it was a cylinder intersecting a plane. It's a closed loop. So the question is, when you use a circular parameterization, when you made these choices here, you decided what your bounds would be. So for a circle, how long does it take to go all the way around? 2 pi. So for a circular parameterization where you use a t here, it's going to go all the way around from 0 to 2 pi. So if you just want to find the length of that loop, it's going to be 0 to 2 pi. If you used a different parameterization that wasn't a circular parameterization, you'd have to figure out what the biggest and smallest your parameter could be. I think I'm not gonna compute that. It simplifies. Expand, get sine squared plus cosine squared, and simplifies, and we get our answer. Okay, so we did a lot of, I mean, there's two, another way a question like this could come up. So just a comment, since we've kind of stuck on this theme for a while. If I had given you the curve in the first place, I know I've asked questions like this before. So I'm gonna ask a new question here. Zoom out. What if I asked you to visualize this, not draw it, but find a surface that contains all the points? So find a surface, just trying to think of a related question, containing this curve. So back in 13.1, I was, when I write the test, just to tell you what I do, I open up all the homework, and as I write the questions, I make sure my wording matches the homework, because I feel like that's fair, because you've seen the homework. That doesn't mean the homework exam questions are as long as some of the homework, but the wording is similar. Okay, so there is several questions in your homework and me reviewing the last 2 days where it says, tell me something about the surface it's on. So what could you say? There are 3 answers, actually. You could combine these 2 equations, you could combine these 2 equations, or you could combine these 2 equations. All of those would give you surfaces. Probably the easiest surface would be to say, since this is cosine and this is cosine, what can you say about z? Z is what? It's kind of silly because we already know the answer. Z is the square root of 3 times x. So I was saying that this question could sort of be done in reverse. Rather than me give you the surface and you find the curve, I could give you the curve and ask you to find the surfaces. Okay. So that just helps us visualize a little bit. All right, let's get on to something else here. I feel like we.
Wait. Can you?
Yep, please.
Go scroll up a little bit so like both
Yep.
questions are showing at the same time for a second.
Yeah. Yep.
Thank you.
And I tried to distribute this to everybody. Everybody might check in your OneNote. Can you see my writing if you pull it up? You know if that's not the case. Okay. I'm going to jump to something else when we're ready. Kind of a lot of the skills there are very particular to that thing. So I want to make sure we hit some other things. So I'm going to look back at so I would say what we just did. And for the person that asked that question, did I hit part of it at least? They were online.
Yeah, thank you.
Yep. This was, so we did a tangent line, it would say, and then we did another curvature. This is just for me. It's kind of notes later to help me sort of get a snapshot of where we're at. So what are things we haven't hit? We could do some more stuff with lines and vectors. At some point, I'd like to do something with lines and planes. We've been spending quite a bit of time on curves. So we'll look at this one and then we'll see where we're missing. So you might start thinking about things if somebody has particular maybe lines and plane questions. Let's look at spring 24. We'll head back there. Question 1. This parts of this came up in our review yesterday, but maybe not this part. So sometimes giving you a parallelogram or a triangle in 3D allows for lots of vector questions. And I found over the years that you do want to treat each part independently. Just because you're stuck on one part, this is a hard thing to do, but if page 1 on the test goes terrible tomorrow, should it affect page 2, 3, and 4? It does, because we're people, but you have to try to treat the pages independently. I used to coach baseball, and we would tell the students, you strike out 5 times, then you go up to the bat again. I don't know how you forget. I feel like you have to be kind of dumb in baseball. intentionally forget things. So we got to do that. That way. Okay. Don't let any baggage or for previous problems get in the way of writing something down. All right, we have this following thing. We have this point 1, 2, 3. We have this point 2, 3, 5. And we have this vector that points from here to here. One small little strategy on a question like this is you could, before you even read the questions, think about what else can you label now. Sometimes that helps.
We
Like
can
I
find
immediately want to label a whole bunch more things when I read that. So my first comment is, I really want to label D. I know what it is immediately. Why do I know what it is? So this goes to the fact of what a vector is. A vector tells you how to change. And we can find the vector AB, yeah. So if it tells you to get from A to D, you need to go up 3 for X, down 1 for Y, and your Z needs to stay the same. Where's the point D? You go up 3 from X, it started at 1, so it's going to be what? 4. You go down 1 for Y, so this is 1, and you don't change. So this is just a comment, is if you find yourself reading the questions and you're kind of lost, go back and just label a few more things, and then read the question again. I find that we sometimes forget that we bring stuff to the table when we're doing a problem. And so when we're lost, just fill in what you do know. Okay, so I also, yeah, I agree. I'd like to find the vector AB. Somebody mentioned that. AB. Let's do that. So 2 minus 1 is 1. 3 minus 2 is 1. 5 minus 3 is 2. I really want to label the point C now. Now, because it's a parallelogram, you actually also know what this vector is, and you know what this vector is. You don't even need to compute anything new. Why do I say that? Well, because both those blue vectors are the same, and both those orange vectors are the same. So what's the point C? So this is 1, 1. Let's use orange. Let's keep with the color scheme. Blue and orange. What is this? Is that like Syracuse or something? Okay, so we're going to go up 1. So what's this going to be? 4 up 1 is 5. 1 up 1 is 2. 3 up 2 is 5. So that's all stuff that that's just a nice little dance of how do we use points and vectors and what do they mean? Any questions on that piece? That kind of affects lots of things. And sometimes we don't realize we have everything we need. Okay, so part A was what is the point C? Oh, and I have it already. 5, 2, 5. But that was the intention of this question, was to see if you could maneuver your way around the parallelogram. Sometimes it's fun to play. After you've studied quite a bit, you can start to go, what are the other questions? Oh, no. So you cover up the exam and you say, do I have this guy figured out? What are the other questions on this page? Any ideas? What are things I can ask that are related to what we've done? What are things we could find?
area of parallelogram.
We could find the area of this. How would we do that?
Cross product.
Cross product,
1/2.
find the magnitude. I could ask you to find an angle here. How would you find this angle? You would do your 10-star fact using the vectors AD and AB. Okay? I could ask you to find this point right here, or this vector, or this length. What's that all about? I've had people say, how would I know that I'm supposed to use projection? If you see something that's perpendicular to another side, it's a projection question.
Wait,
This
I'm
is a
sorry. Wait, what is the 10-star fact again?
Good question. So the 10-star fact is this: U dot V equals the magnitude of U. I
Oh, it's
call
the
it
angle
10
equation. Okay, wait, why do we
Yeah.
call it the 10-star fact?
Because I put 10 stars around it when we did it.
Oh,
There's no
okay.
real reason
I just
besides
remember the equation. I forget. Okay, cool.
Yeah, so that'd be calling it the 10-star fact did not help, but we use that a lot. So back when we did it in class, I put a bunch of stars around it. So I don't know if we need the 10-star fact here. We need the area of a parallelogram, so we do a cross product. We need to find, I did ask for the angle. I didn't look ahead. We need to find the angle at A. We do a projection. But I think the question was about part A. Did we hit that? In some ways, this is the hardest because you had to realize that you didn't need anything special to do it. Good. Yeah. I'm going to jump back here. So I like that. That was kind of what a vector means. Moving around a parallelogram. Vectors and points. So somebody in general was asking about a projection, which we could talk. I feel like I've done that one on that exam. So maybe I could find another one. Or we could jump to something else. Let's maybe get another round of what are some other particular exam questions people are wanting to look at. I could add to our list and then try to make some decisions on what else to hit. Is this all right? Is this working? Yell at me if you want to see something else or if you want me to overview something instead. So particular questions, you can ask me in the chat or here. It is 11:50, so if you have another class, you're welcome to go. I'm going to stay for another 40 minutes. Spring 23. Don't leave anything blank tomorrow. Check everything you can check. Other questions? We'll wait for the clear out here. Anybody online? So we'll just pause for a moment while you identify questions you might want to ask about. Yeah, thank you. Let me look here. So 2-minute break here as oh yeah, coming back. Spring 19, 1B. Other things, yeah.
Yeah, those require working with normal vector. We don't use those anymore. They're super interesting, but it takes a while to compute all those vectors, and then from that you still have more work to do. So the osculating plane, the osculating circle, the oscillating sphere are useful for sort of thinking about how something curves, but not that nice to compute them.
Yeah, let's talk about intersection. Lovely. Yes, in the back there. Spring 23, 4B. Lovely. Great, yes. Spring 24, 1D. That hits on the projection idea. All right. Let's, just because we were just there, and because it hits projections, we're gonna go out of order here. It's like when the person who ordered the coffee after you gets theirs first. All right, here we go. Spring 24, and then we'll hit some of those other things for sure. Let me extract a couple things here. Just gonna pull this down here. Well, let me do it. Oh well. Nah, I'll just try. So the question's asking about, this is what you're asking about, right? This question? Yeah. So the question says, I'll just draw this picture. I have this vector AD, and I have A, and I have D. Separately, I have this vector AB. I have A, I have B, and I have the vector AB. And it says something about those two. It says there's a point E on the line segment from A to B, and the line is perpendicular and goes through D. So I'm going to exaggerate it a little bit so we can see it even more clearly. So it tells you that this is perpendicular, and this is the point E. And the question asks me for the vector that goes from D to E. So let me give us some of our data. So AD, we know. I need a bigger computer on these days. 3, -1, 0. And AB is 1, 1, 2. Was that what it was? Yes. So let's go through a couple things here. It moves. So my first thought is, I have a fast way to get that length. But I mean, the tricky thing about this question, I would say this is harder than a lot of these, is because if it just asks for the length, it's a really short question. If it asks for the vector, that takes a little longer, but still pretty short. But it doesn't ask for any of those. It asks for the vector DE. So we have to kind of maneuver around a bit. So I have a few strategies. We could try to find E. That's one idea. If we could find E, then we would have our answer, Y. You could just subtract. Yeah. So you could do, it did that because it's the end of the hour. I'm gonna have to restart it probably. There we go. So if I could figure that out, I could do E minus D the way we typically do. So that's one strategy. We can just find the point E. So a comment is there is a way to find the point E. You could find the vector EA. I don't think this is what I did in my solutions. You could find this vector, use the fact that you know what A is. I should have copied this down. A was 1, 2, 3. So if we could figure out what this is, and this is, and this is, then you could figure out what E is. Because you could just add this, just like we did in part A. So that's one strategy. That strategy is kind of direct because AE actually has a name. What is AE, that vector? It's the projection. It's the projection vector. So there's a direct way to do the problem. Is you can use the formula for the projection vector, find that vector, add those numbers onto E, and then find the vector. That's a strategy. I think what I did was kind of step through the process to find this. So let's kind of do it in steps as a review. So I'm going to do the length. And then I'm going to do the vector. Just to review the idea of projections. And here's how they work in general. So if you have two vectors, A and B, and you extend the line that B is on and you go straight over to it, and that's perpendicular. That's a projection. we would say that's A onto B, that picture. B is like the ground. So the formula for that is A dot B divided by whatever you're projecting onto. The vector is what you get if you take that vector B and rescale it to this desired length. That's how I remember those two formulas. Yep. Oh, this is my so this is a general comment of what the formulas are. And now I'm going to do it. So in this case, I'm going from the point D to here. And so if I draw this in terms of vectors, I'm going from this vector, let's just look at the vectors, to this vector. So this is like my lowercase a, and this is like my b in the projection formula. So the b is the thing where the 90 degrees is, the place you're projecting onto. So that's the main thing. And in fact, what I like about the formula is I remember it as follows. I find the two vectors. Those are the two vectors. I take their dot product. So I'm going to do 1, 1, 2, dotted with 3, negative 1, 0. And then I divide by the length of the thing I'm projecting onto. So I'm projecting onto AB. What's nice about this is it avoids you having to do a whole bunch of trig and finding the angles. It's a shortcut formula. So this is 3 minus 1 plus 0 over the square root of 1 plus 1 plus 4. So there's quite a few old exams where I just asked for the length, and that would have been much shorter. So if I say, what is the length of the projection? You would say 2 over the square root of 6. And that's what this length is here. So I would say the vast majority of the time when you're doing projections, that's all you need. And it was an interpretation of what the dot product is. Take the dot product, divide by the vector you're thinking of projecting onto, and that will tell you how much of your vector is in that other direction. So sometimes people say a dot product helps estimate how much one vector is in the direction of another vector. So this was a geometric interpretation of dot products. That's a number. Okay, so let's say we wanted to find the vector that goes from A to B. So like I said, this is really nice. I use this quite a bit. And that's the one, maybe I'll do one more example here, just to emphasize how quickly this can be done. So if you're pulling a wagon this way, 3, 2, and you're pulling it along the ground, 10, 0, this is when you don't even need a formula for. What is this length? Let's just run it again. What's the dot product? 3 times 10 is 30. 2 times 0 is 0. Divide by the length of your ground vector, which is 10, and you get 3. That one I didn't need a formula for. Do you believe that it's 3 over? It's more interesting when the second vector is not parallel to the ground. So let's make the second vector like 5, 4. And what's cool is even with that, it's really fast. You do 15 plus 8, divided by what you're going to project onto. Let's project onto this. The square root of 25 plus 16. So it's 24 over the square root of 41. That's that length. So I just like to do several of these to show you it's actually something that makes our life easier, not harder. A projection. It's that fast. Dot product, divide by the thing you're projecting onto. That's what that is. And it works in 3D. So it's used a lot when you're working with forces. Okay, so back to here. I found that length very quickly. Now let's find the rest of the stuff. So what I've learned is I don't remember any of the formulas. My brain can only hold very little. So I say length is 2 over the square root of 6. And then I just deduce everything from that. You can use the formula as well, but I deduce it as follows. I take the vector AB, which is this, 1, 1, 2. That's this vector, and I rescale it. I make it a unit vector, which is the square root of 1 squared plus 1 squared plus 2 squared. And then I multiply by my desired length. And that comes out to be 2 over the square root of 6 times the square root of 6. You always get the same square roots. It's the same thing there. And so this is going to be 2 over 6 times 1, 1, 2. So let's summarize a few things for this problem. Let's get rid of this for just a moment. And I think the part of the thing is just the fact that there's names. So the name part would be, I always have to think about how the book calls this, the component projection of AD onto AB was 2 over the square root of 6. And that was this length. The vector projection of AD onto AB was what you get when you rescaled that vector. It was this. So it's 2/3, 2/6, 1, 1, 2. And it's just a vector that points the same way as A. That's rescaled. So those are two formulas. If you realize you're dealing with a projection, it's just nice to have those because those are often quick ways to answer things. So that was an over answer. So now to the question. Now we have all these tools at our disposal.
Wait, question. Can you label the triangle? Because I still get confused by like, I get the idea that like AD is getting projected like onto AB, but like where is what located on like the supposed triangle? Like how do you know which one is which kind of in the
Oh, in the formula, that's part of maybe the issue is the formula, but whatever's in the subscript is the base. Kind of like when you talk about log base 2 or log base 3, how we put the number down here. That's the base, or think of it as the ground. So when I say AB in the bottom, that's the ground. That's where the perpendicular is. That's the AB.
Okay, so whatever has the perpendicular like angle on it, then that's
what you're projecting
the ground.
on.
That is the base. Okay.
Yep. So I like that because I find that easy to remember because it means I do the dot product of the order of your dot product doesn't matter. And then I divide by whatever I'm projecting onto. And for me, it's helpful to remember that the denominator ends up being the same thing as the base or the thing you're projecting onto. So that's how I remember it. If you projected AB onto D, that would be totally different. I'll show you here. It would be here. So they're not the same thing. Sometimes they're the same length. Like that one looks like it's almost the same length, but. Okay, so we just figured out that this length is 2 over root 6, and that this vector is, I would call this 1/3 to make it look nicer. 1/3, 1/3, 2/3. So I'm just distributing this 1/3 through. I don't know why. So that's the vector. That's the length. Okay, spent way too long there. So now to the final question. If you wanted the point E, how would you get it? And I didn't label it. I didn't copy over my labeling. So if this right here is E, how would you get it? You need to go from A, which was 1, 2, 3, and you need to walk this far. So E is going to be 1 plus 1/3, 2 plus 1/3, 3 plus 2/3. So if you're using the strategy of subtracting, you could do E minus D to get this. Or there's a faster way, which is if you have two vectors and you want a vector that goes between them, how do you do it? So if this is AD and this is AE, how do you get this orange vector that goes from here to here? You subtract. So you do AE minus AD. And I'm sure that's what I did in my solutions. Okay. So sort of talking through a lot of the times when I've asked projection questions, I just asked for the length, in which case it's a really short question. This was a particularly long one because you had this vector, 1/3, 2/3, and you were subtracting AD. Where did I put AD? Have I gotten rid of it? Darn it. 3. So sorry, I shouldn't have spent so long. I've had a lot of people asking about this, and I've answered a few times, and I just probably made it worse. Okay. That's the piece. The other comment is kind of a different thing here, just because I realized this was another issue that I was seeing. So what does A plus B look like? And what does B minus A look like? And what does A minus B look like? That's related to what I was just saying at the end. So if I gave you two vectors, do we know what those look like? You might think about what they would. Do you want me to draw those or should we move on? What do those look like? So here's A, here's B. Let's draw it again. Here's A, here's B, here's A, here's B. The subtraction to me is the quickest to draw. So this vector is what? It's the vector that goes from the head of B, from the head of A to B. How do you get that? Is that the vector sum or the subtraction? It's subtraction. This is B minus A. This vector right here is A minus B. And if you want the sum, we do that head to tail rule. We draw B again. And this is A plus. So at the end of the question, I used this B minus A idea. That was a strategy. Let's do something else. So I spent way too long there. Okay. And made things worse. So let's look at this one, because that sounds probably as a line in a plane question. Spring 23, 2C. Spring 23. Okay, so we've done some of the other parts. That's 4. Okay. So here's 2 line and plane questions. Maybe we can end up doing both, but the question was about C, so let's start there. So line and plane questions are challenging, but we do have a set strategy here. So let's run through that. Find an equation of the plane that passes through this point and contains the line of intersection of this other thing. So we want, let's put this over here. We want a plane. So find an equation of the plane. So that's what's guiding me here. And then we're doing this. And we're looking for a point and a normal. And in a moment, I'm going to think about what I was given. And we can even talk about our general strategy for all of these. So there's the template you can sort of set up. In terms of strategy, maybe I'll say that first because that'll kind of guide us. One of two things happens. After you figure out what you're given, you sometimes are given the normal, in which case you're done. And if not, you're typically trying to find 3 points on the plane. That's not really the goal, but if you can get 3 points on the plane, what can you do with them? Because our goal is to find a normal vector. So how do we use 3 points on the plane? We find 2 vectors. So the real goal is to find 2 vectors that are parallel to my plane. 2 vectors, I'll just say on the plane, and do their cross product. So that's typically the strategy. You do need to read the question and make sure. And there's several steps that goes into that. In order to get the vector AB, you have to subtract. In order to get the vector AC, you have to subtract. You do a cross product. So most of these questions involve subtract, cross product, and I have my normal. Yeah. Yeah. Yep.
To then get the normal vector and put that into. Would that be enough?
It doesn't quite work because that vector you just found points in the direction of the line. And the line is on the plane. So you did find a vector that's useful, but it doesn't point in the direction of the normal. So let's get to that. So I was kind of separating this before we dive in, but I like what you said, which is you could immediately write 0, 0, 2 because you have a point. So this question was all about finding the normal. And so they gave me a point. That's good. And so it's really about deciphering. It's unfortunately, this word is important. It contains this line. So if you're going to draw the line, how would you draw it? So contains means it's on there. Be much better if it was perpendicular. Then we'd be immediately done. The hard part is if you're going to try to draw the intersection of the 2 planes, I can't draw that very well. Like I'll put way back here in space, I've got this plane. I have another plane. I did a bad job, and that continues. So it's hard to draw that, but the moment I see the intersection of 2 planes, which we have here, x plus y minus z is 1, and 2x plus y minus. I pretty much always do the same thing. So your cross product way would give you one, so talking about would give you a vector that points this way, what you were saying. So it's not like a total waste of time, but it still doesn't finish the problem. So in my mind, I think if I could find 2 points here, I will be done. Not done, but I'll have what I need because I already have 1 point right here. So then I will step into my strategy. So because of kind of how I think through it, I rarely do the cross product of those normals. It's not, in some cases that works, some cases that gives us a vector that's useful. If the question was to find the line, that's useful there. But pretty much always, if you're unsure what to do, find 2 points on here because that gives you 3. And so pretty much everything I can think of, when you have the intersection of 2 planes, if you can find 2 points on there, then you can do pretty much anything you want. You just need something that tells you a place to start and a direction to walk. Okay, so that's kind of, if you want to just, whenever you see these words, the intersection of 2 planes, just say, I'm going to turn that into 2 points and be done with it. You're pretty safe. Okay, so I need to find points that work. I would combine these in some way. Maybe I'll do you can either solve for x or y and substitute in. I think I would subtract side by side because I can see that the y's cancel if you do that. So if I subtract side by side and combine, I get negative x plus 0 plus 2z equals 2. So I did this minus this, that minus that, that minus that. Okay, that's right. And the moment I write that, I go, now I get to pick any points I want. They just have to work in there. So I usually pick, so here's 1 point. I'm going to have x be 0. I'm going to figure out what y and z have to be. And then maybe another point is I'll have z be 0. And then I'll throw that in with the point I already know, the 0, 0, 2. And I'll feed it into our strategy. Okay, so let's find those points. So if x is 0, what do we get for z? Get 2z equals 2. So z is 1. Yeah. And then you say then you go back to either one of these. If x is 0 and z is 1, you should get the same y. So I like to plug it into both to verify. So I'm going to get 0 plus y minus 1 is 1. That gives me y is 2. And the other one gives me 0 plus y minus 3 is negative 1. That also gives me y is 2. And then I'm going to find one more. So the one more is when z is 0, I think x is negative 2. So let's plug those in. So z is 0. X is negative. So negative 2 plus y equals 1. So y has to be what? What goes there? We add the 2. I think it's 3. There are lots of ways to sort of make an arithmetic error, but the nice part is at this moment you could check. You could do 0, 2, 1, is it 1? Yes. 0, 2, 1, is it negative 1? Yes. So there's a way we can confirm those points. I compartmentalize my thinking because I know once I get there, I have a strategy. So then you just have to reset and say, I need PQ, I need PR, and I want to take their cross product. So PQ, you can do it in any order, but I'll do negative 2, 1, negative 1. Then PR is 0, negative 2, 1. Once I get done with their cross product, I'll be done. So it's going to be 1 minus 2, negative 2 minus 0, 4 minus 0. So I'm getting negative 1, 2, 4. And again, I wouldn't trust myself, so I would check that it's perpendicular to this. 2, 2, and negative 4, that works. Negative 4 and 4, that works. So then I would type it in, negative x plus 2y. So yeah, sometimes you can have some shortcuts, but if you're unsure, that's the way to go there. Okay, good question. How would you find the x-intercept? So the x-intercept would be where it intersects the x-axis. Which means the y and the z would be 0. So this is asking when this is 0 and this is 0, what's x? So you would solve and get it. Any questions there? So the takeaway from that is the intersection of two planes is something that pops up in a few different places. And typically the strategy when you see that, or a strategy that's pretty darn good and works in almost all situations, is to combine, find 2 points that are on there, and then use those to help you answer the question. Any other questions on this one? Yes. Yeah, I mean, you still could do this and then just use the vector. So if the line was perpendicular, you would use the vector PQ in these spots. But you can also do the cross product method. Yeah, if we see a line in a plane that's perpendicular, that makes it a really short question. In fact, I wonder if that's, let me look at this previous question. Consider the line that contains the point and is orthogonal to the plane. So this is an example of what you're talking about. Yeah. So when I read that, make this a little bigger. It's giving me a plane. Let me make sure I didn't cut off part of it. Yeah. 3, so the plane is 3y minus z equals 10. That means the normal vector is 0, 3, -4. So this is what was given. We're trying to find a line. So what we want is a point and a direction vector. And they gave me the point 5, 0, 0. Okay, so when I read this question and I see this word orthogonal, I'm very happy. Because it's saying that the line is perpendicular to the plane. And so when I draw the line, I'm going to draw like this. And I want a vector that points this way. And they gave me a vector that points that way. So I don't need to do anything else. So yeah, so if the question had been to find the line
Of intersection of two planes, and you have a vector.
the fact that it said contains made it worse. It was parallel. It was like it was on there. All right, that's great. Let's see where we're at here. So that was projections, and this was lines and planes. And Raj left about intersections. Is the person who has spring 19 still here? Yeah. Let's look at that. Spring 19, 1B. Yeah. Okay. So there's a, you weren't asking about this, but now we have a strategy here. Right. So we'd find 2 points. So B has a couple things in it. This was me trying to do a problem of, like, imagine you're sliding down a surface or a curve and you know the acceleration due to gravity, and you want to know how much the acceleration is in the direction we're going. I didn't state it that way, but that's where it comes from. But this question first. Find a vector that has length 4 and is parallel to the tangent line at 3. How did that go? So I do need to find the tangent, the derivative. So here's our function, 10 plus 4x minus x squared. Here's the derivative. And at x equals 3, we get that the slope is 4 minus 2 times 3, which is -2. So this question was about, I have a line with slope -2. That's this line. Oh, yeah. So that, yeah. So the challenge was, how do you find a vector with slope -2? So you use that 1, -2. And then you make it a unit vector. And then you multiply by your desired length. I do remember students getting confused on part B of this question, because if you hadn't done part A, it almost would have made part B easier. Because the fact that because you don't have to use this vector in this part, you could use any vector that points this way. it'd probably be easier to use 1, -2 as your projection because the numbers would come out nicer. You'd say, I'm projecting this onto this. I do their dot product, so it's going to be -9.8 times -2 divided by the length of the projection thing you're projecting onto. So 19.6 over √5. That's probably the setting where I've used projections the most over the time that I've my mathematical career.
Wait, sorry, question. Where are you, wait, I think I missed a step here. Where are we getting the 4 over √5 here?
Oh, so this, let me erase this because this was something separate I was saying. So the square root of 5 is coming from the length of this vector. So it's the length of this vector is the square root of 1 squared plus -2 squared. Yeah, which is square root of 5. And so this, when I write the following, so first we'll kind of step through the pieces. So first we figured out the slope needs to be -2. And that meant that this vector is one example of something that's parallel to that slope, because the ratio is -2. And then I made that a unit vector. So I made that a unit vector by dividing by its length. And then finally, the question wanted it to be length 4. So I wanted it to be 4 times as long as this. 4 times as long. And so I multiplied by 4. Does that make sense? That was kind of a separate part of the question.
Yeah. Okay, that makes sense. Cool. So like 4 is a kind of our scalar in this case.
Yeah, it's what we're trying to. So the strategy when you want a particular length is to first make it a unit vector. If you just multiply by 4 from the get-go, it makes it 4 times as long, and it didn't start out as 1. And so this is like if you want to scale to a certain length. In fact, if you just want to say, what is the formula for scaling to length 4? It would be this. But this could be replaced by whatever you want. Most often we scale it to length 1. And that would be what we call the unit vector.
Thank you.
Lovely. Let's see where we're at. So that was scaling vectors. I think Raj left about the intersection. Somebody asked about spring 23.4. Are you still here? Yeah. Spring 23.4b. Spring 23.4b. Okay, so there was a curvature question, a tangent line question. Good. Do you want to go through both those, or is there? Yeah. So it's asking for the curvature at 0 for this thing, right? So what we need is this curvature formula, r prime of t. There's a, yeah, thanks for coming. There's a practical thing of, there's a way to make our work a little easier. So I'll talk about that, but ultimately it's asking us to compute this thing. So we're going to have to do a cross product. We're going to have to find a length. But before we do any of that, we need to find the derivatives. So sort of, if I was going to give you a procedure for curvature problems, step 1 is to take the derivative. It's typically a good idea to kind of line them up, but let's do that now. So the derivative is 2t 3 -4t. And the second derivative is 2 0 -4. So in general, if you want the formula, you have to do the cross product. But the question did not ask for the general formula. So I'll call this step 2. Plug in your number. So if you plug in your number right after you take your derivative, it makes it shorter because you're just, all the variables go away. So this becomes 0, 3. It doesn't give the general formula, but the question didn't ask for that. So now we need to find a couple things. We need the cross product of these two things. Why is that happening? So let's see, -12 minus 0, 0 minus 0, 0 minus 6. So I get -12, 0 minus 6. Did I do that right? Yes, that matches up. So then the last part is computing the lengths. So you need the magnitude of the cross products. We need the magnitude of -12, 0, -6, divided by the magnitude of the first derivative, cubed. So these curvature questions end up being more about, can we use a vector formula? It's going to be this messy thing. So 12 squared plus 6 squared over, this is just 3. Square root of 3 squared cubed. On a test, I mean, if I was doing this on a test, I would maybe just so it's easier to type in or write down 144 plus 36 over 27. What is that? 70. 144 plus 36. 180. So I would just write the square root of 180 over 27 and stop. So mostly the curvature becomes this complication. That makes sense. It kind of becomes a way for me to test your cross products. But if you try to find the general formula, you'll get the right answer, but it's a little harder. It's more interesting because it'd be more interesting to have the full formula, but the full formula requires you include all the t's. Since the question on a test, that would just be too long. Great question. Yeah. So the definite, so the way there's two things, the way I think about it, which I'll say second, but the definition of this is how much your unit tangent changes. So if you stand at, let's say you're standing at time 0 and you have a unit vector pointing the direction you're going, and then you move forward like 1 inch and you look at your unit tangent, it has moved slightly. The length of how much it's moved, that's what that number is. So it's how much the unit tangent has deflected to the side. It's actually the instantaneous rate, but I like to say 1 inch because that helps me think about it. I say, how much has this changed divided by 1 inch? I find that still not very helpful because that's not the few times where I've like worked with my dad and we had to make a circle, you almost always are given the radius. And so there's a connection between these two numbers. So if you compute the curvature of something, it turns out that 1 over that is what we would call the radius of curvature. And what that means is if you took this number and flipped it over, that takes a bit to prove. Whatever that is, if you made a circle with that radius, that's what your curve looks like at that moment. So that's a much more visual description of like, if you took a circle and you have this curve, you're trying to study. And I just find that a lot more, I think that's more a practical thing. It's just hard to find that circle, but you have a curve. At this moment, you form a circle that is tangent to it and has the same slope and the same curvature. It turns out that if the curvature is I don't know, 0.2. That's a bad choice. If the curvature is 1/5, then this radius is 5. And then it can change a moment later. So like if it's straight, the circle gets bigger and bigger and bigger. So the radius gets really large. In fact, it's infinite if it's straight. If it's a very slight curve, your circle's gigantic. So a large radius means you're doing a slow turn. A small radius is a tight turn. So like if you were to track along the parabola, like the radius would be whatever it is out here, it gets smaller and smaller, and the tightest turn would be here. So for me, that's way easier to think about is, if I were on a circle, how big would the radius be that would be equivalent? But the definition is, how much does my unit tangent deflect if I move a little bit? That's how the curvature is defining that. I don't know enough of the history of why we don't just define it directly in terms of the radius. I think that's because of where it pops up in formulas. Lovely. Just making sure we're not going to be immediately kicked out here. That was curvature. So you wanted to talk intersection a little bit. And then there was a spring 24. Maybe I can do that with, we can look through some exams here. So let me grab a few things here. This is not quite what you're asking, but this is the intersection of two surfaces, a plane and a plane. And the final answer is going to be a line. Now, we have a certain way to do those, but the comment is if it's surface, your final answer is going to be a curve.
You have to just be like 2x equals x equals, I thought that worked though. It's like, when you want to do it, like 2x equals x equals 3u or something? Or is that something you do when you have two curves?
So, I was mostly making a comment that what your answer will look like. So let me say a general thing and then come back to that. So if you have, here are the three situations. I'll make up an example. So you have this 1 minus t, z is t to the third, and you have a surface, x squared plus y equals 4. And the question, so that would be, and I because I'm randomly making these up, might not be nice. I'm making it up. So you're given a curve, you're given a surface. This is like a parabolic cylinder. These ones you just combine, and your final answer is going to be a point, or maybe a couple points. So if you think of a curve moving around, it's going to hit the surface, maybe in 1 or 2 points, and we just straight combine. And actually, what I just wrote probably is not solvable. So let me change it in some way.
The surface you find, have a point.
Yep, and I feel like this is more intuitive than some because you just substitute.
Right. And then that could just be like x squared plus 1 minus t, right? And then you plug that into the x and solve for t, right?
Yep. So if I called, so you'd have t squared plus 1 minus t equals 4. So that's after you've combined. And
then you get the value of t, and then you plug that into the x, y, z to get the point.
Right. So you would solve, in this case, it's a quadratic. So there might be 2 solutions. And then for each one, you would get a point.
And that's when we do any kind of curve.
That's right. So you basically just, the answer is combined. If it's two curves, the answer is also combined.
Maybe different variables though.
But you need different variables if you're trying to find where the paths intersect. Yeah, it's just going to be a point. So this is similar. So if I take the same first curve, t1 minus t cubed, and then I give a second curve, you know, I should say, put something here. Here, it's hard for me to come up with an example on the fly because it's very unlikely they intersect. So the way I would, yeah. So like, the way I would, if I was coming up with this example, I would just make up a number for t, like 1. Let's say I wanted 1 to be the answer. Then this would be 1, 0, 1. And then I would think about how could I make this be the same? How about if a u is 2? If u is 2, that'll make a 1. And then I'm going to do u minus 2. Or maybe I should do something else. And then I will do, and then it needs to be 1. U over 2. So that's how I'd make an example. Yep.
Y.
Yep. You'd have this system of equations. Yeah, and I would call this, yes. In a sense, we already are, we went from lots of variables to 2. So this was a good bit of combining. And then we're just going to combine further. Your kind of ultimate goal when you have a whole bunch of equations and you want to know an intersection is to get it all down to one variable if you can, because then you can solve that one variable problem. So you're going to combine, these two equations actually might be the same. I think if you combine them, you're going to get 0 equals 0. If that happens, that doesn't mean anything's wrong. It just means move on to the next one. Oh, this is bad. I'd have to change this to something we could actually solve. It's not bad, it's a cubic. And we don't have a good way to solve a cubic.
These different variables.
And at that point, you'll have t, you'll have u, and you can plug into either one. It'd be nice to plug into both.
You need to even get, like, do you even need to get value of u if you already have t?
That's a good point. The main issue would be, let's say you find a couple different t values that work. You'd want to make sure it works in all three. Meaning you could have some, like, let's say you combine and you get t could be 2 or t could be 5. And then you go to plug into the third equation and you realize when you plug in 5, like it's not possible, then you would scrap that. So there are situations where like only one of them works. And so I guess if you just get t and immediately plug it in, you're kind of assuming that works for the other equation. So it's probably a good policy to find the corresponding other letter.
So if you did find t though and you found u, would check that you plug either one to the corresponding one. That's right. That's good.
And that's even just good as a check. That it works in both. So those are similar in that your final answer, you basically get one equation with one of your parameters. You just combine, and then once you know t, you plug it in.
And then surface the result equation.
Right. So that I really feel like is something. It does. I mean, you are combining, but sometimes I think about this that it's almost unclear what we want. But we've now seen several examples of what we want is to turn it into a curve. So our final answer will be something with a t, something with a t, something with a t. So it's a very different goal. You're not trying to get it down to, here's the number, this is the point done. The goal is to just describe it in terms of one symbol instead of having so when you have a jumble of equations, if I give you the surface x squared plus y squared is 4, and then I give you y, or let's say.
For these questions, we always begin with equations.
Yeah, I mean, you could have something that's the intersection of more, but I think that we wouldn't. Yeah, that we wouldn't have that now that I think about it. But if somebody handed me these two things and said, I want to study the intersection of those two surfaces, just saying that is not very user friendly because you could start to try to combine them.
But a more clever way to combine is basically what we're doing. Can we come up with three equations that involve one variable that sort of describe both of the things that happen?
And so that's the freedom piece. It isn't wrong to combine, like you could replace this y squared with that y squared. All of those will give you more equations that are true, but they won't necessarily lead to like a one variable equation. And so at this point, we already are, because we're lucky enough that one of them's a circle, we can parameterize it immediately.
Do
And
you
so,
recommend for practicing this just to go through like the case homework, like understand?
yeah, that's yeah, it's more just like how it would be a small part of the test, but it happens in a couple places. One is if I say eliminate the parameter and give me a surface. There were several of those in the homework. Like there was one in the homework that even said, gave you a multiple choice and said, which of these are surfaces it's on? And you had other ones that said, figure out what the picture is, and the way we figure out the picture is figure out if it's on phone, on cylinder. Right. So there are small questions like that, and then the other questions were, I think in that same homework, 13.1, there were ones like this, where it said given two surfaces, find the parameters. And then this just reappeared in 13.3 with that one more question where you're doing R plane, but in order to do the R plane, you had to find it. So it's just one of the ways curves arise is from studying surfaces. You have a couple surfaces, you want to know where they intersect, and there's a whole bunch of ways to describe that intersection. So you have this weird bit of freedom. It's like you're trying to turn it into a one variable problem. It's not always, the truth is it's not always easy or possible, but if we're giving you two surfaces like that, there probably is some quick choice you can make. So it's kind of explaining how could curves arise, the sorts of curves we're seeing. The other way they can arise is the 13.4 stuff, which is you start with acceleration. You start with forces, and then you're actually describing motion. So those are kind of our two big worlds of why do we use vector functions and 3D curves, or how do we study them? One is kind of intersections of surfaces. Another is this motion of an object through space. Motion problems are just harder though, because you have to know to make it accurate. It's harder to find the equations without lots of physics stuff. This is a little easier in the sense that we can find a parameterization if we're just given total freedom to parameterize however we want, and we're not constrained by forces and gravity and everything else. Kind of the way to think about it. Anybody online with any things? I have a class that's about to come in here, so I'm going to close out shortly, but thanks for all your questions and help. That was interesting. I think I only didn't get to one. Yeah. And I'll answer a few. So I'll post this video later this evening, and I'll make some sort of timestamp here. But I think I'm going to head out. Go get them tomorrow. I'll be there for the first. I'm proctoring the 8:30 exam, so I'll be around. But all right. Let's stop share. Let's end meeting.